It is late June 2006, and the president of the International Mathematical Union is sitting across from a man with unkempt hair and long fingernails in a stately mansion overlooking the Neva River in St. Petersburg. He has been talking for 10 hours over 2 days. He is offering the highest honor in all of mathematics, an award given to fewer than 60 people in the history of the discipline. The man across from him solved a problem that defeated every mathematician alive for 99 years. He proved that if the universe is finite and simply connected, there is exactly one shape it can be. And he posted the proof on a free website for anyone to read. The president offers 3 options: fly to Madrid and accept, stay home and the medal will be mailed, or refuse outright. The man tells him he chose the third option before the conversation started. 4 years later, a different institution will offer him $1 million. He will refuse that too. And the reason why is a story that runs through Poincaré's retracted claim in 1904, a 20-year dead end by a geometer at Columbia, a 3-day peer review that should not have happened, and an unattributed passage buried on page 400 of a journal nobody checked. Tonight, that is exactly where we are going. Get comfortable, subscribe if you have not, and if you want more of this kind of thing across physics, mathematics, and the stranger corners of how reality works, that is what the Patreon is for. Stay until the end, because the reason Perelman walked away is not the reason you think it is, and it will change how you look at every institution that claims to be in the business of truth. In 1904, a French mathematician asked a question about the shape of the universe. The question was 6 lines long. It appeared in the final paragraph of a paper that almost nobody outside of mathematics has ever read, published in an Italian journal that no longer exists in its original form. Henri Poincaré wrote those 6 lines, set down his pen, and then added a sentence that has haunted mathematics for over a century. Translated from the French, it reads, "But this question would carry us too far." He died 8 years later. He never answered it, and for the next 99 years, neither could anyone else. That is not the story you were told. The version you heard, if you heard anything at all, is that some brilliant Russian guy solved a famous math problem, turned down $1 million, and disappeared. And that version is technically accurate in the same way that saying the Titanic was a boat that had some trouble with ice is technically accurate. It leaves out everything that matters. It leaves out why the question mattered. It leaves out what the answer actually means for the space you are sitting in right now. It leaves out the century of broken careers, retracted proofs, and professional humiliation that the problem left in its wake. And it leaves out the part that I still cannot stop thinking about, which is what Grigori Perelman saw when he looked at the institution of human knowledge, the system that was supposed to celebrate the greatest mathematical achievement of the century, and decided that the whole thing was so fundamentally corrupt that the only moral response was to walk away from it entirely. Not from the money, not from the fame, from us, from all of us. I need you to understand something before we go any further. The Poincaré Conjecture is not just a math problem. It is a statement about the geometry of reality itself. It says that if the universe is finite, if it closes back on itself the way the surface of a sphere closes back on itself, but in 3 dimensions instead of 2, and if that universe has no holes in it, no handles, no tunnels, nothing you could thread a string through and pull tight, without the string catching on something, then there is exactly one shape it can be. 1, not 2. Not a family of shapes, not a spectrum of possibilities, one shape. The 3-dimensional sphere. And for 100 years, Nobody could prove it. Nobody could confirm that the universe, if it is finite and simply connected, is locked into a single geometric destiny with no alternatives. Perelman proved it. Then he proved something even bigger. Then he refused the Fields Medal, which is the Nobel Prize of Mathematics and has been awarded only to roughly 60 people in the history of the discipline. Then he refused $1 million in cash from the Clay Mathematics Institute. Then he stopped answering his phone. And the last confirmed thing he said to a journalist through the door of his apartment in St. Petersburg was, "You are disturbing me. I am picking mushrooms." That line gets quoted as an eccentricity, a punchline, the reclusive genius who prefers mushrooms to money. But I have spent an unreasonable amount of time with the primary sources on this story, with the actual papers, with the timeline of events between 2002 and 2010, and I do not think Perelman is eccentric. I think he is the sanest person in this entire story. I think he looked at the way the mathematical establishment handled his proof, the way credit was stolen, the way a major journal was weaponized, the way a Fields Medal laureate orchestrated what can only be described as an attempted intellectual heist. And he decided that participating in that system was a form of complicity. And the thing that should unsettle you is not that he walked away, it is the possibility that he was right to. But to understand why, you need to see the whole thing. From the beginning. Henri Poincaré was born on April 29, 1854, in Nancy, France, into a family that was essentially a factory for French institutional power. His cousin Raymond Poincaré would become president of France during the First World War. His father, Leon, was a professor of medicine at the University of Nancy. Henri himself was the kind of mind that appears maybe once a century. The mathematician E. T. Bell called him the last universalist, meaning the last human being who could move fluently across every branch of mathematics that existed in his time. He made foundational contributions to topology, celestial mechanics, the theory of relativity, the philosophy of science, and a field he essentially invented called algebraic topology. He held simultaneous chairs at the Sorbonne in mathematical physics, celestial mechanics, and probability theory. When he died in 1912, the world lost a mind that could hold more of mathematics inside itself than any mind that has existed since. And he almost did not survive long enough to ask the question. In 1870, during the Franco-Prussian War, the Poincaré family remained in Nancy as Prussian forces occupied the city. Henri was 16. He watched soldiers quarter themselves in French homes, watched a foreign army administer his town, and the experience left a mark that would surface later in his fierce French patriotism and his complicated intellectual relationship with the German mathematical establishment, particularly with Felix Klein. In the 1880s, Poincaré and Klein entered a prolonged correspondence about Fuchsian functions that began as collegial exchange and deteriorated into something close to a feud. Klein believed Poincaré had failed to credit German predecessors, particularly Fuchs himself, whose name Poincaré had attached to the functions. Poincaré, characteristically, did not seem to notice the offense he had caused, or if he noticed, did not consider it worth adjusting for. He was interested in the mathematics, not the politics of attribution. But Poincaré's most important contribution to this story was not any single theorem. It was the creation of topology itself. Before Poincaré, the study of shapes was essentially a branch of geometry. You measured angles, distances, areas. The properties that mattered were metric properties dependent on size and measurement. Poincaré realized there was a deeper layer, a layer of properties that survived even when you stretched and distorted the shape without cutting it. He called this analysis situs, the analysis of position, borrowing a phrase from Leibniz. We call it topology. The original analysis situs paper of 1895 was 65 pages long and introduced for the first time the concepts of homology and the fundamental group, the Euler characteristic for higher dimensions, and the Poincaré duality theorem. It was followed by 5 supplements published between 1899 and 1904, each one correcting or extending the previous ones, and each one introducing new ideas that would take decades to develop fully. The entire series reads like a mind working faster than the available formalism can support. Poincaré was inventing the language of topology at the same time he was trying to use it. And the result is a body of work that is simultaneously visionary and riddled with gaps. The 5th supplement, the one containing the conjecture, was the capstone. Poincaré had realized, through 4 supplements of trial and error, that the tools he had built were not powerful enough to answer the question he really wanted to answer. Each time he thought he had the right invariant, the right test to determine whether a space was a sphere, he discovered a counterexample that passed the test but was not a sphere. The dodecahedral space was the final counterexample, the one that forced him to reach for the most powerful tool he had, the fundamental group, and ask the cleanest possible question. Is the fundamental group sufficient to characterize the sphere? The question, phrased that way, was both the product of accumulated failure and an expression of extraordinary mathematical taste. Poincaré had the instinct to identify the sharpest possible question, the one that cut to the heart of what topology could and could not do. And it turned out that the question was so sharp that nobody could answer it for 99 years. A century later, that exact attitude would surface in a Russian mathematician who carried it to its logical conclusion and walked away from everything. Poincaré's working method was itself unusual and worth understanding because it anticipates something about the way the conjecture would eventually be solved. He worked almost entirely in his head. He reportedly spent long periods pacing or sitting, turning problems over mentally, and then wrote out results in bursts of concentrated output. He rarely revised. He produced roughly 500 pages of published mathematics per year for the last 2 decades of his life. His papers were dense with insight and sparse on rigor, full of brilliant leaps and missing details. The 5 analysis situs supplements published between 1899 and 1904, the ones that founded algebraic topology, are famous for exactly this quality. As the CNRS Analysis Situs Digital Project describes them, the ideas abound and rub shoulders with errors. The brilliance and the sloppiness were inseparable. They were products of the same mind, a mind that moved too fast for its own formalism. This matters because the Poincaré conjecture itself was born from one of those errors. Poincaré's 1900 claim, the one he had to retract, was not a casual mistake. It appeared in a major paper in the field he had created, and it was wrong. And the specific nature of the error reveals something about the depth of the problem. Poincaré assumed that homology, the algebraic machinery he had built to classify spaces, was powerful enough to distinguish the sphere from everything else. He was wrong because homology counts holes in a particular algebraic way, and it turns out 2 spaces can have identical hole counts and still be fundamentally different. To see the difference, you need the fundamental group, which tracks not just where the holes exist, but how loops wind around them. Poincaré discovered this distinction by constructing a specific counterexample, the dodecahedral space, and the discovery forced him to ask a sharper question. The conjecture, in other words, was not the product of confident genius. It was the product of failure, of a great mind encountering its own limits and being honest enough to say so. But here is what nobody tells you about Poincaré. He got it wrong first. In 1900, in the second supplement to his masterwork Analysis Citus, Poincaré made a claim. He said that any closed three-dimensional space with the same homology as a sphere, the same algebraic signature in terms of certain topological invariants, must actually be a sphere. He did not prove it. He stated it with the confidence of a man who had invented the field and assumed he understood its limits. And within 4 years, he discovered he was wrong. Not partially wrong, completely wrong. He found a counterexample with his own hands, a space that has all the same homological fingerprints as a sphere, but is emphatically not a sphere. It is called the Poincaré homology sphere, or the dodecahedral space, and it is built from the geometry of the icosahedron, that 20-faced Platonic solid. Its fundamental group has 120 elements. You can wind a loop through it that cannot be shrunk to a point, even though every algebraic test you run says it should be a sphere. Poincaré had to retract his own claim, in his own paper, in a field he had invented. Think about that for a moment. The greatest mathematician of his generation published a major claim in the field he created, and then had to come back 4 years later and say, I was wrong. The test I was using is not good enough. We need a finer instrument. And the finer instrument he reached for was something called the fundamental group, a way of classifying spaces not just by their algebraic invariants, but by the structure of all possible loops you can draw inside them. And once he had that instrument in hand, he could pose the real question, the question that would consume the next century. If a closed three-dimensional manifold has a trivial fundamental group, meaning every loop in it can be continuously shrunk to a point without tearing or leaving the surface, is it necessarily the three-dimensional sphere? That is the Poincaré Conjecture, and the last line of the paper, where he posed it, published in the Rendiconti del Circolo Matematico di Palermo, volume 18, pages 45 through 110, is the one I already told you. But this question would carry us too far. He had no idea. Poincaré could not have known what he was asking. He could not have known that the question would outlive him by 91 years, that it would absorb the careers of some of the finest mathematicians of the 20th century, that it would become one of 7 problems, chosen from all of mathematics to carry $1 million bounty. He could not have known that the answer would require the invention of an entirely new mathematical tool, a machine for smoothing the geometry of space itself that would not exist for another 78 years after his death. And he could not have known that the man who finally answered it would refuse every prize, every honor, every form of recognition the mathematical world could offer, and vanish into a small apartment in St. Petersburg with nothing but a violin and his mother's pension. But perhaps the strangest thing Poincaré could not have known is this: the counterexample he built in 1904, the dodecahedral space that proved his earlier claim wrong, the very space that forced him to pose the conjecture in the first place, would be proposed in 2003 as a candidate for the actual shape of the physical universe. The mathematical object he constructed as a proof of his own error might be the cosmos. That kind of irony is the sort of thing that makes you wonder whether mathematics has a sense of humor and whether anyone is paying attention. Poincaré died on July 17, 1912, from an embolism following prostate surgery. He was 58 years old. He received 51 Nobel Prize nominations between 1904 and 1912. 51. His nominators included Hendrik Lorentz, Marie Curie, Albert Michelson, and Guglielmo Marconi. All of them Nobel laureates themselves. He never won. The Nobel does not consider mathematics. He is buried in the family vault at Montparnasse Cemetery in Paris, and the question he left behind became one of the most famous unsolved problems in the history of human thought. Now I need to stop here and do something that will seem like a detour, but is not. I need to make sure you understand what the word shape means in the context of this conjecture, because it does not mean what you think it means, and the misunderstanding is the reason most people never grasp what Perelman actually proved. In topology, a coffee cup and a donut are the same object. I need you to take that seriously, not as a cute analogy, as a literal, mathematical statement. In topology, two objects are considered identical if you can continuously deform one into the other without cutting, tearing, or gluing. You can stretch, you can bend, you can squish, but you cannot rip and you cannot attach things that were not already attached. Under these rules, a coffee cup with a handle and a donut are the same shape because you can slowly deform one into the other. The cup part of the mug can be squished down into the ring of the handle, and the handle can be thickened into a torus. No cuts needed. This is not a metaphor. This is the definition, and it is the definition that governs the Poincaré Conjecture. When the conjecture says that a simply connected, closed, three-manifold is homeomorphic to the three-sphere, the word homeomorphic means exactly this. You can deform one into the other continuously, without cutting or gluing. The conjecture is asking whether there exists some exotic, three-dimensional shape that passes every topological test, every test of loop contractibility, and yet somehow cannot be deformed into a sphere. Perelman proved that no such shape exists. If every loop in your space contracts to a point, you are living on a sphere, period. But what does every loop contracts actually feel like in 3 dimensions? In 2 dimensions, it is easy to visualize. Take the surface of a ball. Draw any closed curve on it. You can always slide that curve down to a point. It shrinks smoothly to nothing without ever leaving the surface. Now take the surface of a donut. Draw a loop that goes around the whole of the donut, through the middle. That loop is trapped. You cannot shrink it to a point without cutting the surface. It is caught on the whole. That trapped loop is what topologists call a non-trivial element of the fundamental group. The sphere has a trivial fundamental group, meaning every loop contracts. The torus has a non-trivial one, meaning some loops are stuck. Now move to 3 dimensions. You are living inside a 3-dimensional space that curves back on itself, like the surface of a sphere, but with an extra dimension. You cannot see the curvature any more than an ant walking on a basketball can see the curvature of the basketball. But you can test for it. You can send out a rope in any direction, let it travel through the space, and if the space is finite and closed, the rope eventually comes back to where it started. Tie the ends together. You have a loop. If you can always reel that loop back in, shrink it to a point, no matter which direction you originally sent it, then your space is simply connected. And the Poincaré Conjecture, now the Poincaré Theorem, says that if your space is finite, closed, and simply connected in this sense, then you are living on the 3-sphere. There is no other option. The shape of your universe is determined. And proving this took 100 years, because the 100 years in between Poincaré's question and Perelman's answer were a graveyard. I want to stop here and tell you what happened to the people who tried to solve this problem, because the human cost is part of the story, and the human cost is something that gets sanitized out of every account I have read. In 1934, the British mathematician J.H.C. Whitehead announced he had proved the Poincaré Conjecture. He had not. He found his own error, which is the best possible outcome for a false proof. But in the process, he accidentally created something called the Whitehead manifold, a strange, contractible three-dimensional space that is not homeomorphic to ordinary three-dimensional Euclidean space. His mistake produced a genuinely new mathematical object. But the conjecture itself was untouched. Christos Papakyriakopoulos, a Greek mathematician working at Princeton, spent decades on it. Decades. His entire adult mathematical life bent toward this one problem. He never solved it, but in 1957, along the way he proved Den's lemma, a result that had been incorrectly claimed to be true since 1910, and that turned out to be a critical tool in three-dimensional topology. He died at Princeton in 1976, still working on the conjecture. He had no tenure. He had no permanent position. He had spent his career as a research associate, living modestly, entirely consumed by a problem that consumed him back. And Papakyriakopoulos was not alone in his dedication. The conjecture attracted a specific type of mathematician, the kind who preferred one deep problem to a broad portfolio. These were not dilettantes or publicity seekers. They were serious topologists who understood the difficulty and chose to spend years, sometimes decades, on a single question because they believed the answer mattered. And the answer did matter, though not in the way most popular accounts suggest. The Poincaré Conjecture is not important because it was hard. Hard problems are common. It is important because it is a statement about whether the simplest possible finite universe has a unique shape. If the answer had been no, if there existed some exotic, simply connected three-manifold that was not a sphere, the implications would have been staggering. It would have meant that the topology of the simplest possible universe was not determined by its fundamental group properties. It would have meant there were hidden degrees of freedom in the shape of reality, extra rooms in the house of possible universes that nobody had entered. The fact that the answer turned out to be yes, that the sphere is the only option, is in some ways reassuring, but it took 100 years and a graveyard of careers to confirm it. There were also claims so embarrassing that the mathematical community preferred to forget them. In 1962, a mathematician claimed a proof and received significant attention before the error was found. In 1979, another attempt circulated informally and absorbed months of checking by established topologists before collapsing. These episodes left scars. By the 1980s, claiming a proof of the Poincaré conjecture had become something close to a professional risk. The problem had a reputation, and the reputation was, this problem destroys people. It invites overconfidence. It rewards brilliance with humiliation. And the gap between thinking you have a proof and actually having one was, in three-dimensional topology, wider than in almost any other field. R.H. Bing, at the University of Texas, was reported by colleagues to alternate 2 weeks spent trying to prove the conjecture, with 2 weeks spent trying to find a counterexample. 2 weeks on, 2 weeks off. For years. Imagine that rhythm. Imagine spending half your working life trying to show something is true, and the other half trying to show it as false, knowing that the problem does not care which direction you approach from. In September of 1986, Colin Rourke and Eduardo Rego announced a proof. They gave a talk at Berkeley. During the talk, a fatal error was identified. The proof collapsed in public, in front of their peers. A salvageable byproduct survived, something about the enumeration of Heegard diagrams, but the conjecture remained. And then, in April of 2002, just months before Perelman would change everything, a mathematician named Martin Dunwoody posted a 5-page proof on his homepage at the University of Southampton. 5 pages for a 100-year-old problem. Within days, Colin Rourke himself, the man whose own proof had collapsed at Berkeley 16 years earlier, identified the fatal flaw. The proof was withdrawn. John Stallings, who proved the conjecture in dimensions 5 and above, but could never crack dimension 3, published a paper in 1965 with the title, How Not to Prove the Poincaré Conjecture. It was a post-mortem of his own failed attempt. The genre of the mathematical autopsy became part of the conjecture's folklore, and the mathematician John Milner wrote that the conjecture tested the temper of the steel of generation after generation of topologists. And here is the thing that needs to be said about all of this. The Poincaré conjecture was not just hard, it was hard in a way that specifically targeted dimension 3. And the reason is deeply strange. Stephen Smale proved the generalized version of the conjecture for dimensions 5 and above in 1961, published in the Annals of Mathematics, volume 74, number 2, pages 391 through 406. He won a Fields Medal for it. Michael Friedman proved it for dimension 4 in 1982, published in the Journal of Differential Geometry, volume 17. He also won a Fields Medal. Dimension 3, the original conjecture, the one Poincaré actually asked about, the one that matters for the shape of the universe we live in, held out for another 21 years after Friedman. Why? Because in higher dimensions, there is room to maneuver. You can slide things past each other. The topology has enough slack that the surgical techniques mathematicians use to cut and reassemble spaces actually work. In dimension 4, Friedman used radically non-smooth methods, techniques that only work in the topological category and produce manifolds so wild they cannot be given a smooth structure. But in dimension 3, the manifold is too tight for the high-dimensional tricks and too complicated for the two-dimensional ones. Dimension 3 sits in a cruel middle ground where neither the freedom of high dimensions nor the tractability of low dimensions is available to you. I want to make sure you feel the strangeness of this, because the fact that dimension 3 is the hardest case is not just a technical curiosity, it is a statement about the mathematical universe we inhabit. In dimensions 1 and 2, topology is essentially solved. Closed one-dimensional manifolds are just circles. Closed, two-dimensional surfaces are classified by their genus, the number of handles, which is just a counting problem. In dimensions 5 and above, Smale showed that the extra room available to the topologist makes the Poincaré conjecture provable by handle sliding arguments, techniques that move pieces of the manifold past each other the way you can slide boxes past each other in a large room. In 4 dimensions, the situation is wild and exotic, with phenomena like the existence of uncountably many smooth structures on 4-dimensional Euclidean space that do not exist in any other dimension. But even there, Friedman managed to prove the topological version using radical methods that exploit the specific strangeness of dimension 4. But dimension 3 resists all of these approaches. The manifold is too constrained for high-dimensional surgery and too complex for low-dimensional classification. Every technique that works in other dimensions either breaks or does not apply. There is a technical point here that I think deserves attention because it illuminates just how strange 3-dimensional topology really is. In dimensions 5 and above, Smale's proof of the Poincaré conjecture uses a technique called the H-cobordism theorem. The basic idea is that if two manifolds are connected by a cobordism, a higher dimensional manifold, whose boundary consists of the two manifolds you are comparing, and if the cobordism is simply connected and has the right homology, then the two manifolds are the same. This works because in high dimensions, you can use a technique called Whitney's trick to eliminate pairs of intersection points by sliding them past each other through the extra-dimensional space. The trick requires at least 5 dimensions, because you need room for the two-dimensional disks involved in the cancellation to avoid each other. In 4 dimensions, Whitney's trick fails because there is not enough room. Friedman got around this by using an infinite construction, building infinitely many layers of Casson handles that converge, in the limit, to a genuine topological handle. The construction is so wild that it cannot be made smooth, which is why the 4-dimensional Poincaré conjecture is proved only in the topological category and remains open in the smooth category. That is a separate, unsolved problem. Whether there exists a smooth 4 manifold that is homeomorphic but not diffeomorphic to the 4 sphere, nobody knows. In 3 dimensions, neither Whitney's trick nor Friedman's infinite construction is available. The dimension is too low for any kind of handle trading or cobordism argument. The topology is completely rigid and completely inaccessible to the techniques that worked in other dimensions. This is why the problem required an entirely different approach, why it required Hamilton's analytic methods rather than the algebraic and combinatorial methods that topologists had been trying to apply for decades. The Poincaré conjecture in dimension 3 was not just harder than in other dimensions. It was a different kind of problem, requiring a different kind of mathematics, invented by a different kind of mathematician. It is as if 3-dimensional topology occupies a unique position in the mathematical landscape, a kind of valley between the tractable planes of low dimensions and the spacious highlands of high dimensions. And the only way out of that valley turned out to be through analysis, through partial differential equations, through Hamilton's Ricci flow. The topologists could not crack it with their own tools. It took a geometer's equation to unlock a topologist's question. And that in itself is remarkable, because it means the shape of 3-dimensional space is connected to the behavior of heat equations in a way that nobody before Hamilton had imagined. The conjecture was hardest in exactly the dimension that matters for the shape of the physical universe. And that is not a coincidence. There is something almost cruel about it. The dimension that matters, the one we live in, the one whose shape determines whether the physical universe is a sphere or something else entirely, is the one where the mathematics is hardest. It is as if the universe chose to live in the one dimension where its own shape would be maximally difficult for its inhabitants to determine. A civilization in 5-dimensional space would have had the tools to settle the analogous question by the early 1960s. A civilization in 4-dimensional space could have done it by the early 1980s. We, trapped in 3 dimensions, had to wait until 2003, and even then, the proof required ideas from differential geometry, partial differential equations, and Riemannian geometry that had no counterpart in the purely topological methods used in higher dimensions. And there is a deeper irony. The reason higher dimensions are easier is that they have more room. More room means more freedom to maneuver, more slack in the topology, more space for surgical operations. But the reason 3 dimensions are hard is the same reason they are interesting. The tightness of the topology is what makes the geometry rigid. In higher dimensions, the topology does not constrain the geometry nearly as much. A 5-dimensional manifold can support many different geometric structures for the same topological type. But in 3 dimensions, thanks to Thurston's vision and Perelman's proof, the topology constrains the geometry almost completely, and in the hyperbolic case, determines it uniquely. So the very thing that made the Poincaré conjecture so hard to prove, the tightness of three-dimensional topology, is also what makes the result so powerful. The hardness and the depth are the same thing. The problem was difficult because the answer is profound, and the answer is profound because the dimension we happen to inhabit is the one where shape and geometry are most tightly coupled. If you were designing a universe and you wanted its inhabitants to have access to the deepest possible geometric truths, but also to have to work the hardest possible to discover them, you would put them in 3 dimensions. It is a feature of three-dimensional topology that nobody fully understood until a man named William Thurston came along in the 1970s and proposed something that made the Poincaré conjecture look like a warm-up exercise. Thurston's Geometrization Conjecture says that every closed three-dimensional manifold, not just the simply connected ones, can be cut into pieces along spheres and tori, and each piece admits exactly one of 8 possible geometric structures. 8, not an infinite family, not a continuous spectrum. 8 specific geometries, each as rigid and definite as the geometry of a sphere or the geometry of a flat plane. Thurston identified all 8 of them. Spherical geometry, which is the geometry of the 3-sphere. Euclidean geometry, which is flat. Hyperbolic geometry, which is the geometry of constant negative curvature. Saddle shapes extending in every direction. And 5 more exotic ones. The product of a 2-sphere with a line. The product of a hyperbolic plane with a line. The geometry of the universal cover of a certain Lie group called SL2R. And 2 solvable geometries called Neal and Saw. The claim is extraordinary. It says the entire vocabulary of three-dimensional shape, every possible way that a finite three-dimensional universe could be locally structured, consists of exactly 8 words. And the Poincaré conjecture is just the first word. If your manifold is simply connected, it must be speaking in the language of the sphere. But Thurston could not prove his own conjecture in full generality. Nobody could. Not until a quiet, methodical man invented a tool that would change everything. Richard Strite Hamilton published a paper in the Journal of Differential Geometry, Volume 17, in 1982. The paper was titled 3 Manifolds with Positive Ricci Curvature. In it, he introduced an equation that does something that should not, on the face of it, make any sense at all. The equation takes the shape of a space, its curvature, and lets it flow, like heat flowing from a hot spot to a cold spot. Except it is not heat that is flowing, it is geometry itself. The equation is written as the partial derivative of the metric tensor with respect to time equals -2 times the Ricci curvature tensor. And what it does is take a lumpy, irregular space and smooth it out over time. Where the curvature is high, the shape relaxes. Where the curvature is low, the shape fills in. The lumps flatten. The distortions even out. The curvature distributes itself more and more uniformly, the way the temperature in a room eventually evens out after you turn on the heater. Hamilton called it the Ricci flow. I want you to feel the strangeness of this. Imagine you have a shape, any three-dimensional shape, possibly wildly irregular, with lumps and dents and regions of intense curvature and regions that are nearly flat. Hamilton's equation lets this shape breathe. It pulses. It reorganizes itself, driven not by any external force, but by its own internal geometry. The Ricci curvature at each point measures, roughly, how much a small ball of material in the space has its volume changed by the surrounding curvature. Positive Ricci curvature means small balls are smaller than they would be in flat space. Negative means bigger. And the equation says, where the curvature is positive, shrink. Where it is negative, expand. Over time, the shape evolves toward uniformity, toward one of those 8 Thurston geometries. The profound thing about this, the thing that I think gets lost in the technical discussion, is what it implies. The Ricci flow is not a physical process. There are no actual shapes flowing in a laboratory. It is a mathematical procedure, but the mathematics treats geometry as if it has a temporal dimension, as if shapes have a future, as if the curvature of a space knows where it wants to go, and where it wants to go, given enough time, is toward one of 8 specific destinations. The space does not just evolve, it seeks its own classification. The mathematics behaves as if 3-dimensional shapes have a destiny. I want to give you a more concrete sense of what the Ricci flow actually does, because the abstraction can make it feel less real than it is. Imagine a 3-dimensional space shaped like a dumbbell. 2 large spherical regions connected by a thin cylindrical neck. If you run the Ricci flow on this dumbbell, the 2 spherical regions which have positive curvature begin to shrink. The neck, which has mixed curvature, gets thinner and thinner. Eventually, the neck pinches down to 0 thickness, and you have a singularity, a point where the curvature becomes infinite. At this moment, Hamilton's surgery procedure kicks in. You cut the manifold at the neck, right before the pinch, and cap off each of the 2 resulting openings with smooth hemispherical caps. Now you have 2 separate spheres instead of 1 dumbbell. You restart the Ricci flow on each sphere. Since the spheres have positive curvature, they shrink smoothly to points, confirming that each piece was topologically a sphere. The surgery decomposed the dumbbell into its component parts, and the flow classified each part. That is the simplest case. The real difficulty arises when the singularities are more complicated than simple neck pinches. When degenerate singularities form, regions where the geometry collapses in complicated ways, or when cigar-shaped singularities appear, long, thin tubes that extend without pinching. Hamilton classified some of these singularity types, but could not handle all of them. He could not prove that the worst-case singularities, the ones that do not look like simple necks, actually do not occur under the flow, or that if they do occur, they can be surgically removed without destroying the topological information you need. This is where Perelman's W entropy becomes critical. The W functional is a quantity that Perelman defined on the space of all possible Riemannian metrics, and he proved that it decreases monotonically along the Ricci flow. This monotonicity is the key. It means the flow cannot cycle. It cannot revisit states it has already passed through. It must always move in one direction, toward lower entropy, toward greater uniformity. And the specific form of the functional gives you control over the local geometry near singularities, which is exactly what Hamilton needed and could not find. The technical sophistication of this construction cannot be overstated. Perelman connected the Ricci flow to the theory of optimal transport, to statistical mechanics, and to the theory of Riemannian manifolds with lower Ricci curvature bounds, all in a single framework. He drew on his earlier work in Alexandrov geometry, the geometry of metric spaces with curvature bounded below, work that might have seemed disconnected from the Poincaré conjecture, but turned out to be exactly the technical background needed. The 6 silent years in St. Petersburg had not been idle. They had been spent building the mental infrastructure for one of the deepest proofs in the history of mathematics. And what Hamilton proved in that first paper was remarkable. He showed that if you start with a closed 3-manifold that already has positive Ricci curvature everywhere, meaning it is already curved in a generally spherical direction, then the Ricci flow, after suitable rescaling, converges to a metric of constant positive curvature, which means the manifold is a quotient of the three-sphere. For that special starting case, the Poincaré Conjecture is true. That was the beginning, but only the beginning, because the Poincaré Conjecture asks about all simply connected three manifolds, not just the ones that are already almost spherical. And when you start the Ricci flow on a general three-manifold, something goes wrong. The flow develops singularities, points where the curvature blows up to infinity in finite time. Thin necks form, like an hourglass being pinched. The space tries to tear itself apart. Hamilton understood this. He spent the next 20 years developing a program to handle the singularities. The idea was surgery. When a neck forms, cut the manifold there, cap off the resulting holes with spherical caps, and restart the flow on each piece separately. The flow continues, potentially forming more singularities, which require more surgeries. The vision was clear. Hamilton could see the shape of the whole program. He knew what needed to be true, but two key obstacles defeated him. He could not prove a certain kind of non-collapsing estimate that would control the geometry near singularities, and he could not classify all possible singularity models. I want to tell you something about Hamilton himself, because his story deserves more than the footnote it usually gets in accounts of the Poincaré Conjecture. Richard Streit Hamilton was born on January 10, 1943, in Cincinnati, Ohio. He earned his PhD from Princeton in 1966 under the supervision of Robert Gunning. His early career was spent at Cornell, and he later moved to the University of California, San Diego, and finally to Columbia, where he held a chair until his death. Hamilton was not, by temperament, a fast worker. He was meticulous, careful, thorough. His papers were long and detailed and beautifully written. His 1982 paper introducing the Ricci flow ran to 51 pages and established not just the equation, but an entire analytical framework for studying it. Over the following 2 decades, he published a series of papers that expanded the framework: classification of singularities, estimates on curvature, partial results on three manifolds with various curvature conditions. Each paper was a substantial contribution. Each moved the program forward, but none of them finished it. By the late 1990s, it was becoming clear to the geometric analysis community that Hamilton's program had stalled, not because Hamilton lacked the ability, but because the remaining obstacles were of a different character than the ones he had already overcome. The non-collapsing estimate in particular required a new idea, not just a refinement of existing techniques. Several mathematicians attempted to help. Seminars were organized. The problem was discussed at conferences, but the breakthrough did not come from within Hamilton's circle. It came from outside, from a man who had left the circle years earlier and was working alone. There is a reading of this story that casts Hamilton as a tragic figure, the man who did everything right and was overtaken at the finish line. I do not think that reading is fair. Hamilton built the road. Without the road, there is no finish line to reach. Perelman himself said this explicitly. He told Interfax that Hamilton's contribution was equal to his own. The mathematical community, by and large, agrees. The proof is the Hamilton-Perelman proof. The program is the Hamilton program. The tool is the Ricci flow, and the Ricci flow is Hamilton's. But the dynamics of credit in mathematics are not kind to the person who builds the road. They are kind to the person who reaches the destination. And that asymmetry, the mismatch between the magnitude of a contribution and the attribution it receives, is precisely what Perelman was objecting to when he refused the Clay Prize. He did not want to be the person who received $1 million for completing a program that someone else had built, not because he was modest, but because he thought the distribution was unjust, and he was not willing to be complicit in an injustice, even one that benefited him. These two gaps are what Perelman filled, and the story of how a young Russian mathematician came to fill them begins with a meeting that would define both their careers. In 1992 or 93, Grigori Perelman attended Hamilton's lectures at the Institute for Advanced Study. Perelman recalled the encounter years later, speaking to Sylvia Nassar and David Gruber for The New Yorker. I really wanted to ask him something. He was smiling, and he was quite patient. He actually told me a couple of things that he published a few years later. He did not hesitate to tell me. Hamilton's openness and generosity, it really attracted me. I cannot say that most mathematicians act like that. Remember that phrase, Hamilton's openness and generosity. It is going to take on a meaning neither of them intended, and it is going to haunt the rest of this story. Perelman wrote Hamilton a letter in 1996, outlining some ideas and suggesting a collaboration. Hamilton did not respond. He did not answer, Perelman said later. So I decided to work alone. Grigori Yakovlevich Perelman was born on June 13, 1966, in Leningrad to Russian Jewish parents. His father, Yakov, was an electrical engineer who would emigrate to Israel in 1993. His mother, Lyubov, was a mathematician who gave up graduate work to raise her children and teach in vocational schools. She taught Grigori to play the violin and instilled in him a love of classical music that he carries to this day. His younger sister, Elena, born in 1976, would eventually defend a doctoral thesis at the Weizmann Institute and now works as a programmer in Stockholm. The backdrop to Perelman's childhood was Soviet anti-Jewish discrimination in academia. Access to elite mathematical education for Jewish students in Leningrad was restricted, gated through competitions where Jewish applicants were held to higher standards. Despite this, Perelman's talent was undeniable. Around the age of 10, his mother enrolled him in Sergei Rukshin's after-school mathematics circle at the Leningrad Palace of Pioneers. Rukshin was a 19-year-old undergraduate at the time. He would become Perelman's lifelong mentor. In 1980, Perelman entered school number 239, Leningrad's elite specialized mathematics and physics secondary school. In July of 1982, at the age of 16, he competed at the International Mathematical Olympiad in Budapest. He achieved a perfect score. Every problem, full marks, gold medal, automatic admission to Leningrad State University. His doctoral work at the Leningrad branch of the Steklov Institute, under the supervision of Alexander Danilovich Alexandrov and Yuri Barago, focused on Riemannian geometry with connections to the theory of Alexandrov spaces. In 1991, he won the Young Mathematician Prize of the St. Petersburg Mathematical Society. Then, on the strong recommendation of the legendary geometer Mikhail Gromov, he came to the United States. A semester at the Courant Institute at NYU in the autumn of 1992. A semester at Stony Brook in the spring of 1993. Then, a 2-year Miller Research Fellowship at UC Berkeley from 1993 to 1995. During those years, Perelman proved the Soul conjecture, a result first posed by Cheeger and Grommel in 1972 that had been open for over 2 decades. He did it in 4 pages for a 22-year-old conjecture. Princeton offered him a position. Stanford offered him a position. Tel Aviv offered him a position. He turned them all down. He also turned down a prize from the European Congress of Mathematicians. And in 1996, he went home to St. Petersburg, to the Steklov Institute, and he disappeared into silence. Not physically. He was still there, still affiliated with the institute, still working. But he stopped publishing. He stopped attending conferences. He stopped communicating with almost everyone in the mathematical world. For 6 years, nobody outside his immediate circle knew what he was doing. Some colleagues assumed he had burned out. Some assumed he was working on something too ambitious to discuss. His friend Gromov, when asked, said simply that Perelman was not someone who talked about unfinished work. Colleagues who knew him in the 90s describe a man of extraordinary focus and almost no interest in anything outside mathematics and classical music. He wore the same brown corduroy jacket day after day. He ate simply. During his years in the United States, he reportedly walked from Manhattan to Brighton Beach to buy specific Russian black bread he considered essential. He let his fingernails grow to unusual length. Robert Greene of UCLA told the New York Times he looked like Rasputin with long hair and fingernails. He hunted mushrooms in the forests around St. Petersburg. He played the violin. I do not think any of this is eccentricity. This is a man who has arranged his life around the removal of friction between himself and the work. Every detail of his existence, the unchanging jacket, the simple food, the refusal to spend cognitive energy on appearance or social convention, is a decision to preserve attention for what matters. And what matters, to Perelman, is the mathematics. And then, on Monday, November 11th, 2002, at 4 in the afternoon, Coordinated Universal Time, a 39-page paper appeared on Arxiv, the open-access preprint server. The author was G. Perelman, Steklov Institute, St. Petersburg. The title was The Entropy Formula for the Ricci Flow and its Geometric Applications. The file was 33 kilobytes. 33 kilobytes. That is smaller than a typical photograph on your phone. The entire argument for solving the Poincaré Conjecture, one of the 7 Millennium Prize problems, a question that had consumed a century of mathematical effort, was contained in a file smaller than a low-resolution selfie. The subsequent 2 papers were similarly compact. Together, the 3 papers total roughly 100 pages. For comparison, the Tao Zhu exposition, that would later attempt to claim a share of the credit, ran to 328 pages, and the Morgan-Tien monograph ran to over 470 pages. Perelman compressed a century's worth of mathematical evolution into 100 pages of prose so dense that the world's best geometric analysts needed 4 years and over 1,000 pages of exposition to fully unpack it. This compression itself tells you something about the nature of Perelman's mind. He was not writing for a general mathematical audience. He was not even writing for geometric analysts of average ability. He was writing for the 10 or 15 people on the planet who could follow the argument at the level he was operating at. And he trusted those people to fill in the details that a more conventional paper would spell out. This is not unusual in mathematics. Many of the field's most important papers are written at a level that assumes expert readers, but Perelman's papers were compressed even by that standard. Key estimates were stated without full proofs. Technical lemmas were left for the reader to verify. The logical structure was clear, but the details required substantial work to confirm. This created an unusual situation. The proof was simultaneously public and inaccessible. Anyone could download the papers from Arxiv, but understanding them required years of training in Riemannian geometry, partial differential equations, and the specific technology of the Ricci flow that Hamilton had developed over 2 decades. The proof was free in the sense that it cost nothing to access. It was not free in the sense that it could be verified without enormous intellectual investment. And that gap between accessibility and comprehensibility is what made the verification process both necessary and politically charged. Because here is what the verification process really was. It was a test of the mathematical community's ability to process a result that came from outside its normal channels. Perelman did not play the game. He did not submit to a journal. He did not cultivate a network of supporters who would champion his work. He did not attend conferences and build consensus. He posted 3 papers and left. And the community had to decide, without any of the usual institutional support structures, whether the proof was correct. To their credit, they did it. Kleiner and Lott began their line-by-line verification within weeks of the first paper's appearance. Morgan and Tien organized a sustained effort at Columbia and Princeton. Mathematicians around the world read the papers, discussed them in seminars, emailed questions to colleagues, and gradually built a collective understanding of the argument. By 2006, 4 years after the first posting, the consensus was clear. The proof was correct. The Poincaré Conjecture was settled. And the process by which it was settled, the open, decentralized, community-driven verification that Perelman's arXiv posting had made necessary, was arguably more rigorous than any journal refereeing process could have been. The irony is that this organic verification process, which worked beautifully for determining the correctness of the proof, failed completely at the task of assigning credit. The same community that could spend 4 years carefully checking every line of a 100-page argument could not prevent a 3-day editorial process from producing a paper titled A Complete Proof with unattributed passages. The mathematical community was capable of extraordinary intellectual integrity and extraordinary institutional dysfunction at the same time, and Perelman, watching from St. Petersburg, saw both. Within days, the paper was being read by every geometric analyst on the planet, and within weeks, it was clear that something seismic had happened. Perelman had not merely made progress on Hamilton's program, he had introduced entirely new ideas, new monotonicity formulas, a new way of understanding the structure of singularities, and he had done it with a technical command that stunned even the experts. The W functional in particular, a monotonically decreasing quantity along the Ricci flow, connected the analysis to statistical mechanics and thermodynamics in a way nobody had anticipated. It provided exactly the non-collapsing estimates that Hamilton had been unable to prove. On March 10, 2003, the second paper appeared. Ricci flow with surgery on 3 manifolds. This was the one that contained the surgery procedure, the way to cut and restart the flow when singularities formed. It was the technical heart of the proof. And on July 17, 2003, the third paper, Finite Extinction Time for the Solutions to the Ricci Flow on Certain 3 Manifolds. This was the killing blow. It showed that under the conditions relevant to the Poincaré conjecture, the Ricci flow with surgery terminates in finite time, with the entire manifold recognized as being composed of spherical or collapsed pieces. The Poincaré conjecture followed as a corollary, and so did the full Thurston Geometrization Conjecture. Think about the scope of that for a moment. Perelman did not just solve the Poincaré conjecture. He proved the entire geometrization conjecture. That subsumes it. He proved that every closed 3 manifold can be decomposed into pieces, each with one of exactly 8 geometric structures. He provided the complete classification theorem for 3-dimensional shapes. He finished what Poincaré started. He finished what Hamilton built. In 3 papers, posted to a free server, with no peer review, no journal submission, and no fanfare whatsoever. He chose arXiv deliberately. He did not submit to a journal. He did not send the papers to Annals of Mathematics or Inventiones Mathematicae or any of the elite journals where a result of this magnitude would traditionally appear. He posted them where anyone could read them, for free, immediately, and he left the mathematical community to figure out whether they were correct. The choice to post on Arxiv, rather than submit to a journal, was itself a statement, though it took most people years to understand what kind of statement it was. The traditional path for a result of this magnitude would be submission to the Annals of Mathematics, the most prestigious mathematics journal in the world, followed by a multi-year refereeing process in which anonymous experts would check every detail. This process confers legitimacy. It also confers ownership, in the sense that the journal, the referees, and the editorial board all become part of the story of the proof. The institution wraps itself around the result. By posting to Arxiv, Perelman bypassed all of this. He made the proof available to everyone immediately, with no gatekeepers, no referees, no editorial board, no institutional imprimatur. The proof belonged to the mathematics, not to any journal or committee. At the time, many mathematicians were uncomfortable with this. Arxiv was widely used for preprints, for sharing work in progress, but it was not considered a substitute for formal publication. A result as important as the Poincaré Conjecture, they argued, deserved the full weight of peer review. Perelman's choice looked to some like arrogance, a refusal to submit to the normal process of verification. But in retrospect, the choice looks more like prescience. The three independent verification teams, who spent years checking the proof, did a far more thorough job than any journal referee could have done. The proof was subjected to scrutiny by dozens of experts over a period of 4 years, an intensity of review that no journal process could match. And the result was available to everyone, freely, from the moment of posting. Perelman had invented, or at least demonstrated, a new model for the validation of major mathematical results, one that substituted open community verification for closed editorial gatekeeping. And the model worked. But the model also created a vacuum, and vacuums attract opportunists. In April of 2003, Perelman accepted invitations to lecture in the United States. He visited MIT from April 7th through the 11th. He gave a week-long series of lectures at Stony Brook, the Simons Lectures, from April 21st through the 28th. He spoke at Columbia, at NYU, at Princeton. The lectures were packed. Christina Solmani's handwritten notes from the Stony Brook talks were posted online and remain a primary historical source. Here is something you need to know about those lectures. Perelman answered every question for hours. He was patient, precise, and transparent. When someone pointed out a step that was unclear, he explained it. When someone challenged an argument, he engaged. The mathematicians who attended those lectures uniformly described the experience as extraordinary, not because of spectacle, but because of clarity. Perelman understood every corner of the proof so completely that he could explain any part of it extemporaneously, at any level of detail. There is a detail about those lectures that I think reveals something important about Perelman's character. During the question and answer sessions, which stretched for hours, Perelman was asked repeatedly about the implications of the proof for cosmology, for physics, for the shape of the universe. He consistently deflected these questions. He was not interested in the physical interpretation. He was interested in the mathematics. The proof was a statement about three-dimensional manifolds, not about the cosmos. Whether the universe happened to be a particular kind of three-manifold was a question for physicists and cosmologists. Perelman's job was to establish the mathematical truth, and the mathematical truth was established. This is not arrogance. It is a form of intellectual hygiene that almost nobody in science practices. In an era when every major result is immediately followed by a press release about its implications for technology, medicine, or the fate of the universe, Perelman insisted on saying only what the mathematics actually said, nothing more. He did not speculate. He did not extrapolate. He did not sell. And this raises a question that I think is worth sitting with. What would have happened if Perelman had been a different kind of person? What if he had accepted the Fields Medal, accepted the Clay Prize, used the $1 million to set up a research institute, gone on the lecture circuit, written a popular book, done the podcast interviews, built a public profile? He would have become the most famous mathematician in the world. He would have had resources, influence, a platform. He could have reshaped the incentive structures of mathematics from the inside. He could have used his celebrity to demand reform of the journal system, the refereeing process, the credit assignment practices that he found so repugnant. Instead, he chose silence, and I have been trying to decide whether that silence was the right choice. On one level, Perelman's withdrawal is an abdication. The most morally serious person in mathematics walked away from mathematics, leaving the field to the conformists and the credit claimers and the people who tolerate dishonesty. The system he criticized was not improved by his departure. If anything, it was empowered. The lesson the mathematical community took from Perelman was not, we need to reform our institutions. The lesson was, that strange Russian fellow turned down the money. The system processed his refusal as a personality quirk, not as a critique, and continued operating exactly as before. But on another level, Perelman's withdrawal is the most powerful statement he could have made, more powerful than any lecture or book or institute, because by walking away, he demonstrated something that the mathematical community cannot explain away, that it is possible to do the greatest work and want nothing from the system that is supposed to reward it, that the work itself can be sufficient, that the proof is the proof and the rest is noise, and the existence of even one person who actually lives this way, who actually means it, is an ongoing rebuke to everyone who compromises, everyone who publishes the slightly inflated CV, everyone who cites their own work unnecessarily, everyone who tolerates a 3-day editorial process on a 300-page paper because the senior author is important. Perelman's silence is a mirror, and most mathematicians would rather not look in it. And in a culture that rewards overselling above almost everything else, that refusal was itself a kind of radical act. There is also the question of how Perelman handled errors in his own work. During the Stony Brook lectures, at least one significant gap was identified in his argument. Perelman did not become defensive. He did not minimize the gap. He acknowledged it, explained how to fill it, and incorporated the fix into the argument on the spot. Compare this to the Caoju response to their unattributed passage, which they characterized as an oversight. The contrast is not subtle, but there was someone who did not attend. Richard Hamilton, the man whose program Perelman had completed, the man whose Ricci flow was the engine of the entire proof, did not come to the lectures at Princeton or Stony Brook. He showed up late to the Columbia lecture. He asked no questions, and he left without speaking to Perelman. Perelman told Nassar and Gruber, I had the impression he had read only the first part of my paper. I want you to hold that detail. It is going to matter. After the lectures, Perelman returned to St. Petersburg, and the verification process began. 3 independent teams set about the monumental task of checking every line of Perelman's argument. Bruce Kleiner and John Lott at Michigan began working through the details immediately, posting section-by-section notes online. Their expanded exposition was posted to Arxiv on May 25, 2006, and eventually published in Geometry and Topology, Volume 12, in 2008, running to over 270 pages. John Morgan at Columbia and Gang Tian at Princeton produced their own exposition, posted to Arxiv on July 25, 2006, and later published as a Clay Mathematics Institute monograph. And then there was the third team, Huaidong Cao of Leihai University and Xiping Zhu of Sun Yat-sen University, working under the direction of Fields Medal laureate Xing-Tung Yao. And this is where the story becomes something that should have been front-page news and was instead buried in a New Yorker article that most of the world has already forgotten. In April of 2006, something happened at the Asian Journal of Mathematics. The journal was co-edited by Yao. On April 13, the 31 mathematicians on the journal's editorial board received a brief email from Yao and his co-editor. The email informed them that they had 3 days to comment on a paper by Cao and Zhu. 3 days. The email did not include a copy of the paper. It did not include referee reports. It did not include an abstract. At least one board member asked to see the paper and was told it was not available. On April 16th, Cao received a message from Yao telling him the paper had been accepted. A 328-page paper claiming to provide a complete proof of the Poincaré and geometrization conjectures was accepted by a major mathematical journal in 3 days, without any board member having seen it, without referee reports, and without an abstract. The paper appeared in the June 2006 issue of the Asian Journal of Mathematics, Volume 10, Number 2, pages 165 through 492. Its title was A Complete Proof of the Poincaré and Geometrization Conjectures, Application of the Hamilton-Perelman Theory of the Ricci Flow. Read that title carefully. A complete proof, not an exposition of Perelman's proof, not a detailed verification. A complete proof, as if the proof belonged to Cao and Zhu, and then things got worse. On June 3, 2006, at a press conference in Beijing, the acting director of Yao's Mathematics Institute assigned credit percentages. Hamilton, he said, contributed over 50%. The Russian, Perelman, about 25%. And the Chinese, Yao, Zhu, and Cao et al., about 30%. Those numbers add up to more than 100, which tells you something about the rigor being applied at that press conference. Yao himself added, given the significance of the Poincaré, that Chinese mathematicians played a 30% role is by no means easy. It is a very important contribution. This was June of 2006. Perelman's papers had been posted 3 years earlier. 3 teams had been verifying them. Every expert in the field understood that the proof was Perelman's, built on Hamilton's program. And here was a Fields Medal laureate holding a press conference to claim his protégés deserved 30% of the credit for an expository paper that had been rammed through peer review in 3 days, without anyone on the editorial board even seeing it. But the scandal had not yet reached its peak. In August of 2006, a comparison emerged. Pages 400 through 402 of the Cao Zhu paper, specifically Step 2 in the Proof of Theorem 7.1.1, were found to be essentially identical, line for line, with a passage in Kleiner and Lott's online notes. The passage had been copied without attribution. Cao and Zhu published an erratum in the Asian Journal of Mathematics, Volume 10, Number 4, December 2006. They stated they had overlooked the fact that the argument was in fact based on the work of Kleiner Lott. They apologized for the oversight. An oversight. That is the word they used for copying another mathematician's work without attribution in a paper claiming to provide the complete proof of a Millennium Prize problem. On December 3rd, 2006, Cao and Zhu posted a revised version to Arxiv with a new title, Hamilton-Perelman's Proof of the Poincaré Conjecture and the Geometrization Conjecture. The word complete was gone. The abstract now described the paper as a detailed exposition of a complete proof due to Hamilton and Perelman. Joan Berman, writing in the January 2007 notices of the American Mathematical Society, said the affair had given the mathematical profession a very public and very bad black mark. Sylvia Nassar and David Gruber published their full account in The New Yorker on August 28, 2006, under the title Manifold Destiny. Yao's attorney sent a 12-page demand letter to the magazine. The New Yorker stood by the article. No lawsuit was filed. And Perelman, what did Perelman say about all of this? He told Nassar and Gruber, "It is not clear to me what new contribution did they make." Apparently, Zhu did not quite understand the argument and reworked it. Asked whether he was outraged, he said, "I cannot say I am outraged. Other people do worse. Of course, there are many mathematicians who are more or less honest. But almost all of them are conformists. They are more or less honest, but they tolerate those who are not honest." I want you to sit with that sentence. Almost all of them are conformists. They are more or less honest, but they tolerate those who are not honest. That is not the observation of an eccentric. That is a moral diagnosis. It is a man who has applied the same precision to evaluating human institutions that he applied to classifying three-dimensional singularities. And his conclusion is that the mathematical community is not broken because of its worst members. It is broken because its honest members do not confront the dishonest ones. Now imagine you are Perelman. You have spent 6 years in near total isolation, working on what you believe to be the most important problem in topology. You have succeeded. You know you have succeeded, not with the tentative hope of someone submitting a paper, but with the bone-deep certainty of someone who understands every line of the argument. You post 3 papers. You fly to the United States. You give lectures. You answer every question. You return to St. Petersburg. And you wait. 3 years of other mathematicians working through your arguments line by line. This is reasonable. The proof is long, dense, and touches on some of the hardest analysis in modern mathematics. You are patient. But during those 3 years, a Fields Medal laureate is directing 2 of his students to write an exposition of your proof. And they are not merely writing an exposition. They are writing a paper with the title, A Complete Proof. And the journal is accepting it in 3 days without anyone seeing it. And at a press conference, credit is being assigned. That gives you 25%. And the paper contains a passage copied from another team's notes without attribution. And then the prizes come. In May of 2006, a 9-member committee voted to award you the Fields Medal, the highest honor in mathematics, given every 4 years to mathematicians under 40. You were 40. It was your last year of eligibility. Sir John Ball, president of the International Mathematical Union, traveled to St. Petersburg to persuade you. He met you at a conference center in a stately mansion overlooking the Neva River. He spent 10 hours over 2 days. He proposed 3 alternatives: accept and attend the ceremony in Madrid, accept and stay home, the medal would be sent, or refuse entirely. You told Ball from the very beginning that you had chosen the third option. On August 22, 2006, at the International Congress of Mathematicians in Madrid, the citation was read. You were not present. You became the only person in history to decline a Fields Medal. The reaction from the mathematical world was a mixture of bewilderment and grudging respect. Some mathematicians saw the refusal as a principled stand against the commodification of intellectual achievement. Others saw it as a symptom of psychological instability, a man unable to cope with the attention his work had generated. The media, predictably, went with the eccentric genius narrative. Headlines focused on the refusal of the prize, not on the reasons for it. The story became about the refusal rather than about what the refusal was responding to. But there is something else that happened in Madrid that rarely gets mentioned. At the same ICM ceremony, on August 24, 2006, John Morgan of Columbia University gave a lecture in which he declared that Perelman's proof had been thoroughly checked. He stated that the three verification teams had independently confirmed the validity of the argument. The Poincaré Conjecture was no longer a conjecture. It was a theorem. Science magazine would later name the proof its breakthrough of the year for 2006, the first time the magazine had ever given that honor to a piece of pure mathematics. Think about the timing. In the same week, at the same conference, the mathematical community simultaneously confirmed the greatest proof of the century and failed to deliver the medal to the person who produced it. The proof was celebrated. The person was absent, and the absence was not an accident or a scheduling conflict. It was a deliberate, moral statement by the one person the mathematical world most wanted to honor. You told Nassar and Gruber it was completely irrelevant for me. Everybody understood that if the proof is correct, then no other recognition is needed. And I am not interested in money or fame. I do not want to be on display like an animal in a zoo. And it is not people who break ethical standards who are regarded as aliens. It is people like me who are isolated. And your mentor, Mikhail Gromov, when asked, said, "To do great work, you have to have a pure mind. You can think only about the mathematics. Everything else is human weakness. Accepting prizes is showing weakness." 4 years passed. In May of 2000, the Clay Mathematics Institute in Cambridge, Massachusetts had designated 7 Millennium Prize problems, each carrying a $1 million prize, announced at the Collège de France in Paris on May 24, 2000. The Poincaré Conjecture was one of the 7. On March 18, 2010, the Clay Institute announced Perelman had met the criteria. A conference was held in Paris in June. Perelman did not attend. On July 1, 2010, the Clay Institute announced he had declined the prize, $1 million. He told Interfax, to put it short, the main reason is my disagreement with the organized mathematical community. I do not like their decisions. I consider them unjust. He also said that he considered his contribution no greater than Richard Hamilton's. And here is the detail that ties everything together. Remember how Hamilton did not respond to Perelman's 1996 letter? Remember how Hamilton did not attend his lectures? Remember how Hamilton left the Columbia talk without speaking? And now Perelman, being offered $1 million, is defending Hamilton's credit. The man who ignored him is the man he is protecting. Because Perelman's objection was never personal. It was structural. He was not angry at Hamilton. He was angry at a system that would give one man $1 million and overlook the man whose ideas made the proof possible. That is not eccentricity. That is moral clarity of a kind that makes most of us uncomfortable, because it implies that we are the ones who have the problem, not him. The Clay Institute, left with the money and no recipient, used it to establish the Poincaré Chair at the Institut Henri Poincaré in Paris a position for early career mathematicians funded for 5 years. Jim Carlson, then Clay president, noted the chair was inspired by the Miller Fellowship that gave Perelman the freedom to develop his ideas at Berkeley. The $1 million Perelman refused was redirected to give others the same freedom that had allowed him to work. In late 2005, Perelman had resigned from the Steklov Institute. He explained, "As long as I was not conspicuous, I had a choice, either to make some ugly thing or, if I did not do this kind of thing, to be treated as a pet. Now, when I become a very conspicuous person, I cannot stay a pet and say nothing. That is why I had to quit." The word he uses is pet. He perceived that the mathematical establishment was willing to exhibit him as long as he played the role they wanted. The brilliant Russian who proved the big thing, the ornament on their shelf, and he refused, not because he was antisocial, because he was honest. Since 2005, he has lived with his mother in an apartment in St. Petersburg. He has not held a paid academic position. He has not published. The last credible account of a journalist attempting to contact Perelman comes from 2012. Brett Forrest, writing for GQ, traveled to St. Petersburg and tracked down his apartment building. Through the intercom, Perelman reportedly said he was not willing to talk. He had said everything he wanted to say. There have been sporadic reports since then. Russian media in 2014 claimed Perelman was working in nanotechnology in Sweden. This report was unverified and is widely considered inaccurate. Yakov Ilyashberg, a Stanford mathematician who knew Perelman, told reporters in 2007 that Perelman had confided he was working on other things, but that it was too premature to discuss them. Persistent rumors in the mathematical community suggest he may have been thinking about the Navier-Stokes problem, another of the 7 Clay Millennium Prize problems. If true, the man who solved one Millennium Prize problem may be working on another, in complete isolation, with no intention of ever claiming the prize. But the more likely reality is simpler. He is a man who did the work he was called to do. He completed it. He made it freely available. And then he stopped, because for him the work was the point and the work was done. He did not withdraw from mathematics because he was broken by the scandal or crushed by the attention. He withdrew because he had finished. The conjecture was proved. The geometrization was established. The classification was complete. What remained was not mathematics. It was ceremony, and ceremony did not interest him. And Hamilton. I want to close the Hamilton thread properly because his story does not end the way most people assume. After Perelman's proof was posted, Hamilton could have responded in several ways. He could have publicly acknowledged Perelman's achievement and embraced the completion of his own program. He could have collaborated on the verification. He could have written the definitive historical account of the Ricci flow program from its inception to its resolution. Instead, he was largely silent. He continued to teach at Columbia. He continued to work on geometric analysis. He received major prizes, including the Shaw Prize in 2011 and the Steele Prize in 2009, both of which explicitly cited the Ricci flow and its role in the Poincaré proof. When Hamilton did speak publicly about Perelman's work, he was gracious. There is no public record of Hamilton claiming that Perelman's contribution was less than it was, or that the proof should be attributed differently than the consensus view. The credit dispute that Perelman cited as his reason for refusing the Clay Prize was with the Clay Institute's process and with the Yao Cao Zhu episode, not with Hamilton personally. But the silence between them remains the emotional center of this story. In 1996, Perelman wrote Hamilton a letter proposing collaboration. Hamilton did not respond. In 2003, Perelman gave lectures on the completion of Hamilton's program. Hamilton did not attend, or attended briefly and left without speaking. In 2010, Perelman refused $1 million, partly because Hamilton was not being adequately credited. And on September 29, 2024, Hamilton died at 81 in Manhattan. They never collaborated. They never co-authored a paper. They never, as far as the public record shows, sat down together and discussed the proof that bears both their names. Two men separated by age and temperament and geography, connected by a differential equation and a shared devotion to the geometry of three-dimensional space. And they never had the conversation. I do not know why Hamilton did not respond to that 1996 letter. Maybe he was busy. Maybe he was protective of his program. Maybe he simply did not see the potential in Perelman's ideas at that stage. Whatever the reason, the non-response set in motion a chain of events that ended with Perelman working alone for 6 years, producing 3 papers that completed Hamilton's life's work, and then walking away from mathematics entirely. If Hamilton had responded, if they had collaborated, the proof might have appeared earlier or later or in a different form. The scandal might never have happened. Perelman might still be publishing. The history of mathematics might look different, but it does not look different. It looks like this: a letter unanswered, a proof completed alone, a prize refused, a door closed, and a question about the shape of the universe that turned out to be inseparable from a question about the shape of human institutions. And Richard Hamilton, the man whose Ricci flow program made the proof possible, died on September 29, 2024 at a hospital in Manhattan at the age of 81. He received the Shaw Prize in 2011, the Steele Prize in 2009, and numerous other honors. He and Perelman never reconciled, never collaborated, and never, as far as the record shows, had the conversation that mathematics needed them to have. Now I want to come back to the mathematics one more time, because there is a layer underneath this story that I have been building toward. The Poincaré Conjecture tells you the shape of the simplest possible finite universe, but the Geometrization Conjecture tells you something far more sweeping. It says that every possible finite three-dimensional shape is built from exactly 8 geometric pieces. And in the generic case, the hyperbolic case, something even more remarkable is true. Mostow-Prasad rigidity, proved independently by George Mostow and Gopal Prasad, says that for hyperbolic 3 manifolds, the topology completely determines the geometry, not just the type, the exact geometry, the volume, the distances, the angles, everything. The shape of the manifold fixes its geometry down to the last decimal place. There is 0 wiggle room. This is unique to 3 dimensions. In 2 dimensions, a surface can be given infinitely many different hyperbolic metrics. The shape does not determine the geometry. In 4 dimensions and above, things are even less constrained. But in 3 dimensions, and only in 3 dimensions, the topology locks the geometry in place completely. 3 dimensions, the number of spatial dimensions we actually live in, the number that matters for the shape of the physical universe. And in that number, and only that number, the shape determines everything about the geometry. I do not know how to think about that. Maybe it is a coincidence. Maybe it is telling us something about why 3 spatial dimensions exist at all, about the relationship between mathematical rigidity and physical reality. I have spent weeks with this material, and I still do not have an answer. But it is the kind of fact that should be discussed far more widely than it is. I want to be precise about what this rigidity means, because it has implications that go beyond abstract mathematics and into the physical structure of the cosmos. If our universe is a closed hyperbolic 3 manifold, which is one of the possibilities allowed by Thurston's classification, then Mosto rigidity tells you that the topology of the universe would determine its volume exactly, not approximately, exactly, to infinite decimal places. The volume of the universe would not be a free parameter that could be set by initial conditions or tuned by the physics of the Big Bang. It would be a topological constant, as fixed and determinate as the number pi. You could, in principle, compute the volume of the universe to arbitrary precision from purely mathematical considerations without making a single physical measurement. The size of the cosmos would be a theorem, not an observation. That is a staggering idea. In every other branch of physics, the fundamental constants, the speed of light, the mass of the electron, the gravitational constant, are empirical. They are measured, not derived. Nobody knows why they have the values they do. But if the universe is a closed hyperbolic three-manifold, then at least one fundamental quantity, its total volume, would be mathematically determined. It would not be a fact about physics. It would be a fact about topology, a consequence of the shape. And even if the universe is not hyperbolic, even if it is flat or spherical, the geometrization theorem still constrains it. A flat three-manifold, for instance, must be one of a small number of specific types, each with a specific fundamental domain and a specific group of symmetries. A spherical three-manifold must be a quotient of the three-sphere by a finite group acting freely, and these groups are fully classified. The menu is finite. The options are known. And here is a thought that I have not been able to shake since I started researching this. The classification of three-dimensional shapes is finished. The list is complete. There are 8 geometries, and every finite three-dimensional shape is built from them. This is a permanent result. It will not be revised. It will not be extended. It will not be overturned by new data or new experiments or new theoretical frameworks. It is a mathematical theorem, proved with logical certainty, and it will be true as long as the axioms of mathematics are consistent. Compare this to physics, the standard model of particle physics. Our best theory of the fundamental forces has been revised, extended, and questioned continuously since its formulation in the 1970s. General relativity, our best theory of gravity, is known to be incomplete because it is incompatible with quantum mechanics. Every physical theory is provisional, subject to revision, potentially wrong. The speed of light could, in principle, turn out to be slightly different from the value we measure. The age of the universe could be revised by future observations. The number of fundamental forces could change if a new one is discovered. But the number of Thurston geometries cannot change. The Poincaré Conjecture cannot be unproved. The classification of three manifolds is fixed forever in a way that no physical fact can ever be. And the man who fixed it, who provided the permanent answer to one of the deepest questions about the structure of reality, is the man who walked away. As if proving something eternal was enough, and everything temporary, the prizes, the institutions, the money, the fame, could be left behind without loss. Maybe he understood something about the relationship between the permanent and the temporary that the rest of us have not figured out yet. Maybe when you have proved something that will be true for longer than the stars will burn, the question of whether to accept a medal at a ceremony in Madrid seems genuinely, not performatively, irrelevant. Maybe a man who has seen into the permanent structure of three-dimensional reality cannot bring himself to care about the temporary structure of human institutions. Or maybe I am reading too much into this. Maybe he is just a man who wants to be left alone. Maybe the mushrooms really are enough. But the proof is still there, on arXiv, in 33 kilobytes, available to anyone who wants to read it. And the 3-sphere is still the only simply connected finite shape in 3 dimensions. And the 8 geometries are still the only geometries. And those facts do not need a ceremony or a check or a medal or even an audience to be true. They are true whether anyone is listening or not. Whatever shape the universe has, if it is finite and closed, it is on a list that Perelman's proof completed. We do not know which item on the list is ours. The observations are not yet precise enough to tell us. But the list is finished. That is what Perelman gave us. Not the answer to which shape reality has, but the guarantee that the answer, when it comes, will be on a list that is complete and will never need to be extended. And here is where it connects to what we can actually observe. In 2003, the same year Perelman posted his final paper, Jean-Pierre Luminet and colleagues published a paper in Nature, volume 425, pages 593 through 595, proposing that the shape of the universe might be the Poincaré dodecahedral space. That space, the exact space Poincaré invented in 1904 as a counterexample to his own earlier incorrect claim. The space that led him to the fundamental group, the space that led him to the conjecture, the space that led to a century of failed proofs, the space that led to Perelman. That space might be the cosmos you are sitting in. Luminet argued that the dodecahedral space better explains certain anomalies in the cosmic microwave background radiation, specifically the suppressed quadrupole and octupole moments, the unexpectedly low power at the largest angular scales. The Planck 2018 data is consistent with a flat universe within tight error bars, and the dodecahedral model is no longer favored. But it is not formally excluded either. The topology of the universe remains an open question. There is something else about the dodecahedral space that deserves attention. If you lived in it, you could in principle verify the topology observationally. Because the space is finite and closed, light rays wrapping around the space would create patterns in the cosmic microwave background, ghost images of the same primordial fluctuations seen from different angles. Luminet and his colleagues computed these patterns precisely. They predicted specific correlations between temperature fluctuations at large angular separations, correlations that would be present in a dodecahedral universe and absent in an infinite flat one. The WMAP satellite data showed some of the predicted features, particularly the suppressed quadrupole, but not clearly enough to be definitive. The Planck satellite, with its superior resolution, narrowed the constraints further. The data is consistent with flatness, but consistent with is not proof of. The error bars on the curvature parameter still allow a universe that is very slightly positively curved, very slightly closed, very slightly dodecahedral. And here is the part I find most unsettling. If the universe is the Poincaré dodecahedral space, then we are living inside the counterexample, the mathematical object that Poincaré constructed in 1904 to prove himself wrong. The thing he built to show that his own earlier claim was false would be the geometry of existence itself. The error would be the universe. The mistake would be home. There is something in that thought that I cannot quite articulate. Something about the relationship between human fallibility and cosmic structure that feels important even if I cannot say exactly why. And that means something worth pausing over. Perelman proved that the toolkit for classifying all possible shapes is complete. He proved that the 8 Thurston geometries are the only options. But nobody has told us which option we are living in. The mathematical scaffolding is finished. The building itself has not been started. Poincaré asked his question in 1904. Perelman answered it in 2003. But the deeper question the one the conjecture was reaching toward, is: what shape is reality? That question remains unanswered, and the man who gave us the tools to answer it is in an apartment in St. Petersburg, picking mushrooms. I keep thinking about what Gromov said. To do great work, you have to have a pure mind. You can think only about the mathematics. Everything else is human weakness. Accepting prizes is showing weakness. Maybe Perelman is not the anomaly in this story. Maybe the anomaly is everyone else. Maybe the apparatus of prizes and prestige and $1,000,000 checks and ceremonies in Madrid is not about recognizing achievement at all. Maybe it is about the rest of us, about our need to feel we are participants in the story of knowledge, that we can clap for the genius and share in the glory. And maybe Perelman looked at that apparatus and saw it for what it is: a performance, a ritual that serves the audience, not the performer. The organized mathematical community. That is the phrase he used. I do not like their decisions. I consider them unjust. He was not talking about any one decision. He was talking about the structure, the system that allows a 3-day peer review of a 328-page paper, the system that allows expository work to be rebadged as original proof, the system that allows percentages of credit to be assigned at press conferences, the system that rewards the people who play the game and punishes the people who refuse. Papakyriakopoulos spent decades at Princeton with no permanent position. Perelman spent 6 years in silence. Hamilton spent 20 years building the tools. And when the dust settled, the headline was about how much of the credit belonged to whom, and a 300-page paper was accepted in 3 days without anyone seeing it. This is a story about what happens when the apparatus of human knowledge encounters someone who cares about truth more than the apparatus does. The apparatus could not process him. It tried to give him medals and money and positions and prestige, which are the only tools the apparatus has. When he refused all of them, the apparatus declared him eccentric and moved on. But the proof remains. The proof does not need the institution. It does not need the journal. It does not need the ceremony in Madrid. It does not need $1 million. The proof is correct, or it is not. 3 independent teams spend years verifying every line. It is correct. The Poincaré Conjecture is a theorem. The Geometrization Conjecture is a theorem. The shape of 3-dimensional reality is classified. And the man who did it is in St. Petersburg. Perelman said, if the proof is correct, then no other recognition is needed. That is not humility. It is metaphysics. It is a claim about the nature of mathematical truth, that it exists independently of the people who discover it, that it cannot be owned, distributed, divided into percentages, or enhanced by a medal, that the proof is the proof, and everything else is noise. Poincaré wrote in Science and Method in 1908 that the mathematician does not study objects but relations between objects, and that it is a matter of indifference if the objects are replaced by others, provided the relations do not change. The truth of a theorem is not about the symbols or the paper or the journal. It is about the relations, the logical structure, the thing itself. And Perelman, more than any mathematician alive, seems to have believed this, not as a professional philosophy, as a way of life. There is one shape for a finite, simply connected universe. There are 8 geometries for all finite 3-dimensional shapes. The proof has been posted, verified, and confirmed. It will be true long after every institution, every journal, every prize committee, and every human being is dust. Henri Poincaré asked whether his question would carry us too far. It carried us 100 years, through Whitehead's retraction and Papakyriakopoulos's lifetime at Princeton. and Rourke's public collapse at Berkeley and Dunwoody's 5-page overreach, and Hamilton's 20-year program, and Perelman's 6 years of silence, through a 3-day peer review, and an unattributed passage, and a press conference where the percentages summed to more than 100, and the scandal at the Asian Journal of Mathematics, was not an isolated incident. It was a symptom of a deeper problem in the way mathematics and science more broadly handles questions of credit and priority. The priority system in mathematics, the norm that says the first person to publish a correct proof receives the credit, is supposed to be a meritocratic mechanism. It is supposed to ensure that the person who does the work gets the recognition. But in practice, the system is gamed constantly. Expository papers are written to claim partial credit. Survey articles are published that subtly reframe the contributions of others. Seminar speakers take results they learned from unpublished preprints and present them in ways that blur the line between exposition and original contribution. Perelman's case was an extreme example of this gaming, made visible by the magnitude of the result and the profile of the players. But the underlying dynamics operate at every level of mathematics, from graduate students to Fields medalists. The incentive structure rewards claiming credit over acknowledging it. It rewards publication volume over publication depth. It rewards institutional affiliation over independent work. And it punishes exactly the kind of behavior Perelman exhibited, sharing ideas freely, posting results without claiming priority through traditional channels, and refusing to engage in the credit game. The fact that the man who solved the Poincaré conjecture walked away from mathematics is not just a biographical curiosity. It is an indictment. The system lost its most important participant because the system could not offer him the one thing he actually wanted, which was honesty. He did not want money. He did not want fame. He wanted the mathematical community to be honest about credit, honest about process, and honest about the difference between original work and exposition. And when he found that the community could not or would not provide this, he left. That should haunt everyone who works in mathematics. It should haunt everyone who works in any field where credit and recognition are the currency of advancement. Because if the system is structured in a way that drives away the best people, the people with the highest standards, the people who care most about the truth, then the system is not selecting for quality. It is selecting for tolerance. Tolerance of corner cutting, of credit inflation, of the slow erosion of standards that Perelman diagnosed with surgical precision when he said they are more or less honest, but they tolerate those who are not honest. Through a Fields Medal declined and $1 million refused, and a door in St. Petersburg that stayed closed. It carried us to a theorem that classifies the shape of reality itself, and to a man living quietly with his mother, and to the possibility that the person who understood the shape of the universe most completely is also the person who understood the shape of our institutions most clearly. Both shapes, it turns out, are fixed. Neither has alternatives. There is one more thing I want to say before I let this story end, and it concerns you. You have been listening to a story about topology, about the classification of three-dimensional shapes, about a conjecture posed in 1904 and proved in 2003. And you might be thinking, this is a story about mathematics, about mathematicians, about institutions. What does any of this have to do with me? Here is what it has to do with you. You exist in three-dimensional space, not 4, not 5, not 11, as some string theories propose for the full dimensionality of reality. The space you walk through, the space your neurons fire in, the space between your eyes and this screen, is three-dimensional. And Perelman proved that the classification of that space, the complete catalogue of every possible shape it could take, is governed by exactly 8 geometries, no more, no less, forever. That means The space you occupy right now is one of a finite number of possibilities. The room you are in, the city, the continent, the planet, the solar system, the galaxy, the observable universe, the whole of spatial reality as far as it extends, is topologically constrained by a theorem. The shape of the space between any 2 points in the universe is not arbitrary. It is not random. It is not the product of chance or accident or the whims of initial conditions. It is a mathematical fact, as fixed as the digits of pi, as permanent as the prime numbers. And the person who established this fact, who proved it with rigorous certainty, who gave you the guarantee that the space you live in is classified and known, is a man you will never meet. Who does not want to meet you? Who does not care whether you know his name or understand his work? Who turned down every prize and every honor your civilization could offer? And who is right now, as you listen to this, living in a small apartment in St. Petersburg with his mother? I have spent weeks with this material. I have read the papers. I have read the biographies. I have read the scandal reporting. I have read the primary source interviews, the few that exist. And the thing I keep coming back to, the thing I cannot resolve, is the gap between the permanence of the mathematics and the impermanence of the institutions that were supposed to safeguard it. Perelman's proof will be true for longer than the solar system will exist. The Fields Medal ceremony in Madrid is already a footnote. The Cao Zhu paper with its unattributed passage is already a cautionary tale told to graduate students. The $1 million prize money, redirected to fund a chair at the Institut Henri Poincaré, will run out in a few years if it has not already. Everything temporary has faded, or is fading. The proof remains. And I think that is what Perelman understood. Not as an intellectual position, not as a philosophical argument, but as a lived reality. He understood that the proof is the only thing that lasts, that the medals and the money and the press conferences are sand, that the mathematical structure of three-dimensional space will still be classified by 8 geometries long after every human institution has been forgotten, and that devoting even a single hour of his attention to the temporary apparatus of recognition was an hour stolen from the only thing that matters, which is the work itself. Most of us cannot live that way. Most of us need the prizes and the recognition and the institutional validation because most of us are not certain enough of our own work to let it stand alone. We need other people to tell us it is good because we are not sure. Perelman was sure. He was sure because he understood every line of the proof, because he could answer every question about it extemporaneously for hours, because the logical structure was complete and he knew it was complete. And once you are that sure, once you have that kind of certainty, what exactly would a medal add? If the proof is correct, then no other recognition is needed. That sentence is the most important thing anyone has said about mathematics in the 21st century. And it was said by a man who then stopped talking. Perelman chose the mushrooms.